In this example, I think we looked at this projection a couple of lessons ago. I think it's in the 4th lesson. We project any vector x to the plane z equal to the plane z equal x, y minus x. And this plane I can rewrite as x minus y plus z equals 0. It passes the origin. And the normal vector v is 1, negative 1, 1. Okay, now you see this graph. To solve this equation, ax equals 0, from the graph, I'm really looking for any variables. If I project to the plane, this is a projection plane matrix, projection matrix. If I project to the plane, then you get the image. This image must be 0, origin. So that's the problem. To solve this system, really I want to find the vector whose projection image is only the origin. Now you can guess what kind of vector have this property. Or in another word, if the light always comes down perpendicular and you want the shadow be a point. So it's clear if you project this normal vector will become 1 point at the origin. So that must be the solution in geometric point of view. But still, let's do it by Gauss-Jordan algorithm. Step 1, we write this coefficient matrix. And we write at the right hand 0 on the other side of this straight line. Well, you compare the example 1 we discussed, or not, the example 2. Oh, you realize this is precisely the same left side. The only difference is on the right hand, we changed the constant 3 to 0. And used to be 3 here, but now it's 0. So we do the same operation. First, swap the 2 rows, make 1, 1, 1 in the first corner. And then I just need to add the first row to the third row, negative twice of the first row to the second row. I got these 2 zeros. And then I start with 1 and make this equal 0. And what I'm going to have is this matrix. What this matrix tell you? It simply tell you you only have 2 equations, x2 plus x3 equals 0, x1 plus twice x2 plus x3 equals 0. Well, you know how to solve that. You get a free variable. So now I changed the name from x2, x3 to yz because that's easy for me to write to prepare the slides. But anyway, let me write it back into x2 plus x3 equals 0. You let the x2 equal t because you have 1 free variable. Then your x3 will be negative t. Put into the first equation, x1 plus twice x2 plus x3 equals 0. And then x1 plus 2t minus t equals 0, x1 equal t. So you got t, t, negative t, and t. So this is your solution. I factor out the t. So what does that mean? This solution simpler mean it passes the origin because you don't have a constant in the front, means you have 0, 0, 0 on the front. And there's a straight line parallel to 1, negative 1. Now, I wanted you to recall where you have seen this vector. Now, back to the graph. This vector is precisely the normal vector. So, the solution in algebra just confirm what we observed in geometry. The only vector whose shadow is a single point is this normal vector. And a normal vector, I simply write into a straight line because the length really doesn't matter. So that's our first example. What you need to remember is we really have one freedom. Look at this, one freedom and two independent equations, 3 variables. Well, let's look at the next one. Well, the next system, let's check carefully. The first equation, 2x plus y minus c equals 0. And the second one really is twice of the first one. If you look at multiply 2 to the first one, you get the second one. The third one is really negative 3 of the first one. If you multiply negative 3 to the third one, you get the same. So if you find this system only have one equation, you really don't need to use any matrix method or anything. You just start to take advantage of your free variables. So I write that z equal to x plus y, and I have 2 choices. I let the x equal t, I let the y equal another name s. T and s are independent. And then what I got at z? Z is 2t plus s. Then my solution will write as t as 2t plus s. But the good way to write is t take it out, 1, 0, 2 left here, and the s take out, and 0, 1, 1 left because this 0, 1, 1. And I write into t times a vector and s times another vector. So let's go back to the graph. 1, 0, 2 is a point here. That's a point A. And then this is a 1 vector, no, 2, it's a point here, right here. That's 1 vector, V1. And 0, 1, 1 is another vector, V2. And your solution basically is the plane past these 2 vectors. If you remember in geometry, past 2 vectors, or say passing 2 crossing lines, you have a unique plane. Now you get the plane. And the real solution is a plane with 2 freedoms. You can free to move in anywhere in the plane. If you pick the proper s and the t, it will fill the whole plane. So that's a little bit different. You have infinite many solutions, but this is more than the previous example. Instead of get a straight line, now you get a whole plane. So let's summarize the 3 examples first. Then we're going to do a little more deep connection of the algebra and the geometry. Number 1, all homogeneous systems have a solution. Why? Because 0, 0, 0 is always good for the system. Number 2, we look at the number of free variables. The number of free variables really equals the difference between the number of variables and independent equation. That's a little bit hard on you. What means independent equations? The only way I can explain right now is if you follow Gauss-Jordan algorithms, how many lines, rows, are not all zeros. And those left over non-zero rows is the number of independent equations. If you look at planes in the 3D, independent means they're not parallel. If two of them are parallel, they are dependent. So if you have a system with 3 variables, if the inverse exists, then you have a unique solution. You have no free variable. You got a unique solution. That's our first example. If you have one free variable, like the t in the second example, you really got a straight line, infinite many solutions on the straight line. If you got 2 free variables, you got a infinite many solutions on the plane, on a plane.